Yeah, just 1 minute more, so they can also start on time.
Sure.
So welcome everyone to this session 2, stream 2. We have 3 very interesting talks in this session covering the form verification aspects. And the first one you described as discovering deadlocks in a memory controller IP. This will be presented by Emrah and also Roger, if I'm right, correct? From u-blox and
Yes.
Yeah, that's right. Yeah.
Okay, so please introduce yourself and also.
Okay, thanks. Yeah,
start.
Yeah, I'm Roger Slava from OSCE. I'm here along with Emrah Armagan from u-blox, and it's our pleasure to present this case study on behalf of the entire development team from u-blox, as well as the formal verification team from OSCE. I think deadlocks in verification of designs and proving that they're deadlock free is something that a lot of people across the industry struggle with, and they have to face that quite often. And if that's you, then I hope this presentation will be helpful to you. I'll turn it over to Emrah to get us started, and then I'll join in a bit later. So Emrah, take it away.
Okay. So welcome to our presentation, as Roger made the introduction. So I will slightly go through our agenda today. We will share with you the deadlock verification challenge that we faced in u-blox. And Roger will explain us the formal methodology for discovering the deadlocks. And throughout this presentation, we will share with you the memory controller case study.
Emrah, sorry, your slides are not in presentation mode, please.
Oh, really?
No. It was before, now it's not anymore.
Is it now?
No. Okay, how about I'll just share and I'll click through for your slides, Emrah.
Okay, that's a better idea. Yeah.
Okay, cool. Okay.
So yeah. Okay, thanks a lot. Yeah. So, and we will conclude our presentation with our results and findings throughout this project. Next slide, please, Roger. Yes, so a short introduction about u-blox. u-blox was founded in 1997 as a spin-off from Swiss Federal Institute of Technology. And u-blox is a global provider of leading positioning, wireless communication and short-range communication technologies as integrated circuits, modules, and services. As u-blox, we enable OEMs to reliably locate and connect not only people, but also devices. u-blox is a fabless company owning the full IP, focusing on R&D and customer relationships, and all manufacturing is outsourced. Next slide, please. So yeah, as we explained, we will go through the design deadlock conditions. So the deadlocks in IC design occurs when there's a circular weight condition. And we listed here that cyclical dependency, mutually blocking processes, and mostly as a result of some of those, forever waiting for resources to be freed. So just to give you some example from SoC level, if you have a kind of cyclical dependency between 3 blocks, like block A is waiting for a response from B, B is waiting for a response from C, and block C is waiting for a response from block A. It can lead to some handshake mechanism issues, and these cyclical dependencies may lead to deadlock conditions. We also can see in some deadlock conditions that resource allocation or shared usage of resources can lead to deadlocks, such as if we have 3 blocks sharing 2 resources with locked accesses, and if these resources are not freed at the right time or during the right sequence, 1 or more blocks will be locked forever, waiting for resources or handshaking mechanisms to be completed. Just 1 slide back, Roger. Please. No, back. Okay, so we can say that there are deadlocks in SOC level and IP level. In SOC level, we can say that multiple blocks are involved, and in IP level, multiple FSMs will be involved. And we all know that some deadlock conditions may occur due to software application dependencies that the designers or verification engineers never anticipated that sort of usage, and software teams are using that sort of sequences and causing unwanted deadlock conditions. Next slide, please. Yes, so what we can understand from the headline is we have a lot of challenges with dynamic deadlock verification. And we know that there is no direct methodology targeting deadlocks only. And in the absence of deadlock targeted mechanisms or verification methodologies, especially in simulation world, we will be running thousands of iterations with a lot of test sequences, structures, but we are in the hands of randomization, and we are in the hands of defined use cases or cover groups. And we all know that sometimes in simulation world, finding a deadlock can be a lucky find. And even if we use emulation and FPGA prototyping, these things, these tools or methodologies can increase our performance or efficiency, but still we are bounded with our defined use cases or scenarios. And we also know that most of the deadlocks are rare scenarios, which has dependency to some timing of sequences with a special occurrence with dependency to each other sequence. So we can say that these deadlocks are pretty simulation or emulation resistant. And we can also say that because of the limitations on timing and resources, if definition of coverage may or may not guarantee the absence of deadlocks in our designs. Next slide, please. So yes, now we come to our use case or case scenario. We will be verifying, or we will be describing the DUT, which was a memory controller IP. This memory controller IP was designed to be used in a mobile SoC. As we can see from here that it communicates with multiple masters like CPUs, DMAs through its AXI interface, and it responds to requests from these masters. It arbitrates, contributes, or let's say, after arbitration, this AXI front-end part provides this information to the controller side, which will be handling the memory transactions accordingly. And we can say that it will be supporting multiple channels of the AXI, and it will be handling the handshakes through the 5-pos we can see here. So we can see a lot of deadlock worrying cases when we look at the AXI front end. And just to list some of them here, we can say that any read path stalls due to read after write logic can lead to deadlocks. Spurious read requests can lead to deadlocks, and incorrect volume of read data requested or provided from one side or the other side of this equation can lead to deadlocks. Next slide, please. So we can see here as the second important part of our memory controller IP is the asynchronous queues. So this part is responsible for the, let's say, data sharing or command sharing in between the AXI frontend and the controller PHY sections. And we can say that since those two parts will be working with different clocks, clock domain crossing will be an issue on this part of the design. And if we need to list the main contributors for the deadlock worrying cases here, we can say that any corrupted commands can lead to deadlocks. Data not being cleared out from one part of this equation, which will build over time and cause resourcing problems, can lead to deadlocks, or any data byte dropped can lead to deadlocks. As I said at the beginning, that the other side will be waiting forever for that lost data information. Next slide, please. And finally, the controller PHY side. This part is mainly responsible for providing all these commands and data to the memory interface with defined protocol standards. It's also very critical at this point of time that any commands dropped, not executed through the controller PHY can lead to deadlocks. Or if the controller PHY part provides extra data, this can also build up over time and lead to some resource allocation issues. Or if any data is dropped throughout this process through controller PHY, can lead to AXI frontend issues waiting forever that data to arrive. Yeah. Thanks, Roger. And I think it's now your turn to describe us the formal methodology.
Sure. Okay. Thanks, Emrah. Thanks for that introduction. To set the stage for this, I want to first go over the formal capability maturity model, which describes like the wide spectrum of things you can do with formal verification. And what it also describes is like 5 levels of organizational formal capability. So at level 1, it's the easiest level. It's fully automatic formal. So you just run it on your design. It gives you results right away. And there's some things you can do to target deadlocks even at this level. So the tools will find where you have dead end states and state machines and that kind of thing. The next level are the formal apps, and this is where deeper formal analysis is done on a very small slice of design behavior, such as, for example, connectivity checking signals or checking control and status register behavior. And there are also some apps targeting deadlocks. The next level is ABV formal, where designers write their own properties, RTL assertions. Typically, verification engineers may also add interface properties, but these properties tend to be very local. They're targeting specific design structures or signals at the interface, and typically run in without a lot of constraints. So if you get a proof, that's great, but if you get a lot of false failures, typically, don't focus on those. And then we go to level 4, and level 4 is block level sign off. Here we're functionally verifying an entire block. We're replacing block level simulation with formal sign off. And there's a big difference between levels 1, 2, and 3, which are mainly focused on bug hunting. And level 4, when you get to level 4, here we're starting to replace functional simulation for major units of designs, such as load store units or of a CPU or a Mac receiver block in a communications device, those kind of blocks. And that's a significant difference. So there's quite a bit of difference in methodology that goes into level 4. Beyond that, level 5, it targets even larger problems at the issues of at system level, at full SoC level. And again, we can use levels 4 and 5 to target either block level deadlocks or system level deadlocks. And the focus of this case study, again, is on level 4. So we're looking at block level deadlocks, deadlocks that are occurring within the memory controller design itself. Now, just to explain a little bit about the level 4 methodology. So at level 4, we have this methodology which is often called the 4 C's. It consists of end-to-end checkers, constraints, coverage, and complexity. Those are the 4 C's. The checkers are a little different than the checkers at level 3 because they are the end-to-end checkers, much like a scoreboard in simulation. They monitor the inputs, the design, they predict the output, but they're written in a way that's very formal friendly. They're written with certain techniques that allow them to be used in formal and to get deep analysis in formal. We also have constraints, which we need in order to reduce or eliminate false failures. We need to constrain the formal analysis to the legal input space. But here we also have to worry about validating those constraints to make sure we're not over-constraining and potentially missing bugs. And when we talk about taking these large blocks of designs and verifying them end-to-end with formal, we're always going to run into complexity barriers. We're always going to have that third C of the methodology there at the bottom, where we need to use some techniques, typically abstraction models, to overcome the complexity. And finally, just like in simulation, we have coverage metrics, completion, and to sign off. And that's also part of level 4 methodology. So that's just sort of an introduction, just to sort of define that landscape of all the things you can do with formal and where we are on that spectrum. And now we'll go over how we applied that to the memory controller. So the first thing is that we partitioned the DUT. We partitioned the DUT along the logical boundaries according to the 3 main components that Emrah described earlier. So we have the AXI front end, we've got the asynchronous queues, and the phi. Then we developed the test plan, and the test plan is basically an English list of checkers, which describes all the properties for each of those 3 DUTs that we need to verify. And we defined, in this case, because we're trying to discover all the deadlocks in the design, we defined forward progress checkers. These are key checkers that are required to verify the design for deadlocks. And just by way of example, let's look at this one. So this says that if there are any pending read requests that are accepted by the AXI front end, then the read valid on the response side should assert within a finite time duration. So this is checking the forward progress of a read request through the system and generating the response and propagating that back to the bus master that sent the request. Now, forward progress checkers are key, but they're also correctness checkers that can help us find deadlocks. In the design, if there's a functional problem that occurs, sometimes it'll eventually lead to the deadlock. But if we can spot that functional problem earlier, sometimes we find the root cause of the deadlock before the deadlock is actually even observed. So in this case, for example, I'll just highlight this one checker, which says that for a read request, the number of words that's actually requested by the command sent to the async queue from that AXI front end block must match the number of words, the same size of number of words that was received at the AXI interface. So if, for example, fewer words were sent in the request downstream and fewer words received, then the AXI front end would be left waiting for the remaining words of data forever and maybe get into a deadlock condition. So you can see how that kind of check would also be helpful. So I mentioned the forward progress checkers are key. Let me just look at that. Let's look at that in a little bit of detail. What is a forward progress checker? So again, here's this checker which checks that when the read request comes in, the response should be provided back within a finite time duration. So how do I define this? Well, I'm going to build some modeling logic with a build this modeling logic with a counter, this cycle counter, okay? And this counter says, if I have pending read requests in the system, if I don't have pending read requests in the system, then just keep the counter at 0. And if I get a read response coming back, then I also want to reset the counter to 0. And if I have any back pressure from the downstream side, from the memory side of the system, then I'm just going to hold the counter at its current value. And if I have a read after write hazard condition, then that read cannot make progress either, because it's waiting for a write to complete. So again, I'm going to hold the counter at its current value. Otherwise, I can increment the counter by 1. Now, I can define a property which on this counter, right? So my modeling logic models the counter, and my property says, if I've reached this timeout value, which is a parameter that it could be set based on the depth of the pipelines in the system. If I reach the timeout of the counter, then I must have the response in that cycle. Otherwise, something is stuck somewhere in the request or response path through the AXI front end. Similarly, we defined a list of checkers for the async queues. We defined checkers for the command queue, the write data queue, the read data queue. I'll just highlight one checker here, which is the POP interface protocol on the write data queue. And this checker says that when a POP is requested from the queue, all of the data which corresponds to the command that is generating that POP must be available at the POP side of the queue. And we'll see how this checker was very useful to us a little bit later on. Okay, I also mentioned that constraints validation is a key part of the methodology, so just want to talk about that a little bit. So whenever we make some assumptions at the input of our design under test for formal, we want to verify those assumptions as assertions on the neighboring blocks. So we can run those as assertions in formal if we're running formal on the neighboring block, or at least at minimum, we could run them in simulation when we're running a higher level simulation, maybe system level simulation, and get some coverage of that assertion. If the assertion fails on that neighboring block, then that indicates that we've got an over constraint on our design under test, or we've got a bug in the neighboring block. So here, let's look at constraint validation of how we use that in this particular case. Like, for example, we had constraints that we applied to the controller phi block, and we verified those on upstream logic. Let's look at the POP interface protocol example. So this says that whenever the command is being processed, whenever a write command is being processed by the controller and it pops data from the write data async queue, then all the data should be available at the POP side of the queue. So whenever the POP valid is asserted, POP ready should also be asserted. POP ready is, so there's an assumption that's made that POP ready will always be asserted. POP ready is this equation which says that the occupancy of the queue is greater than the POP data word size. Okay, let's look at a few results from our work on this case study and some of the bugs that we found. And just to again set the stage for this, we want to describe how we classify bugs. Now, we classify bugs on two orthogonal axes. On the horizontal axis here, you see basically the corner caseness of the bug. On the very right, we have the simulation resistant, very highly simulation resistant bugs. And on the left are the easier bugs, the low-hanging fruit. Then we have the vertical axis, which defines the impact of the bugs. So the ones at the top are very high impact, the ones at the bottom, low impact, easy workaround, the ones at the top, showstoppers, right? And it's these bugs in the top right quadrant that we want to target with level 4 formal. These are the deadlock bugs that are going to cause the design to have some serious performance problems that require, a reset to get out of the deadlock. And they're also very difficult to find through all the methods that that Emrah described earlier. Okay, and so let's look at a couple of examples. This first example of a simulation-resistant high-impact bug that we found was had to do with the read after write hazard logic. So here we see, here we see one write request, AW0, coming into the system, and the system is waiting for the write data to arrive. Meanwhile, a read request for the same address comes in, and hazard read after write hazard is detected, so that read request is blocked. Then another overlapping write comes in. Now we see that the data for the original write arrives, and so that first write can make progress. Now we expect the read to be able to make progress. However, the read after write hazard logic is once again blocking that read due to AW1, which was a younger write. Now we can see how this younger write should not be blocking the read, and a continuous stream of younger writes to the same address would block that read indefinitely. And also at the system level, if we have a bus master that's waiting for the read data to come back for AR0 in order before sending the write for AW1, then the entire system would be deadlocked. Okay, we have another example of a bug, but I'll
sorry,
skip
Roger.
that one
So we have only 4 minutes left.
Yeah, I'll just pass back to Emrah to wrap up. Yeah.
So thank you, Roger. So what we can conclude here throughout our study or deadlock finding, hunting through formal methodologies, we've shown that level 4 formal methodology is very effective at finding simulation-resistant deadlock scenarios, and it's very efficient for the use of resources for finding hidden deadlocks. And here we can say some numbers about effort, and not written here, but I want to share with you some personal experience working with OSCE team is that there's a misunderstanding or misinterpretation about formal verification methodologies, like them being just push button. But working with OSCE has taught me, or I had the experience now after working multiple times with them, is that if you have the right experience, finding the deadlocks is easier and you can do it more efficiently, but it's never a kind of push button methodology. So thanks a lot. And if you have any questions, we will be happy to answer.
Thanks for your presentation. So do we have any question? Maybe we can start. So you have also some strategy to support the user to generate the properties, because you showed these 4 C's, but also you see from the checker side. So usually the one mindset, usually the simulation guys have some issues is to how to write or to formalize the properties. So do you have any approach to support the user in this direction?
Yeah, so we don't have any kind of automatic tool for this. Like OSCE is not a tool company. We're just we're a services company, so we focus on the methodology and delivering the formal sign-off services. So yeah, like those kind of checkers that I described, like the forward progress checkers and correctness checkers that are the end-to-end checkers, they're not something that you can automate in a push button way. As Emrah said, it kind of requires certain expertise to understand the requirements of the design and then to map those to properties and develop the property set, and also to make the property set formal friendly. Like you need to write the properties in specific ways with techniques that allow deep formal analysis.
Yeah, fine. Further questions? Not yet. So I'd like to thank you for your presentation. It was really interesting.